Hello, my name is Fred Klink, and I'm going to be speaking about the fundamentals of the electrospray process. Electrospray is the most widely used interface for LCMS in today's market. The reasons for this are varied, and we'll talk a little bit about that towards the end of this presentation. But my primary goal here today is for you to understand, one, how electrospray works, what goes on in the electrospray interface, and two, to understand some of the very basic parameters which users have to control in order to get the best success with electrospray. Well, if we look at an electrospray interface, it's a very simple device. We have an HPLC column which feeds the effluent from that column through an inlet capillary. That capillary is in the atmospheric pressure region of the interface. So this atmospheric pressure region is a closed region, but it's not evacuated. It isn't under vacuum. It's simply atmospheric gases are present. On the opposite side of the schematic diagram on the screen, that is on the right-hand side, there's a capillary opening of some sort, and this varies from one manufacturer's design to another. But this capillary opening then leads eventually to the mass spectrometer through an initially low vacuum or low pressure region, and then on into the high vacuum region of the mass spectrometer. Flowing counter to the direction that the ions travel is a counterflow of a heated drying gas, and this is typically nitrogen. With this nitrogen drying gas, with the nitrogen nebulizing gas, which may or may not be present depending upon the design of the electrospray interface, and the atmospheric gases already present in the atmospheric pressure region, this is largely nitrogen. Most of the oxygen and other gases have been displaced by the use of nitrogen. What actually makes this an electrospray interface, however, is the presence of a high voltage power supply or high voltage which has been applied from the inlet capillary to the inlet to the mass spectrometer across this atmospheric pressure region. And when we apply high voltage to a capillary which is carrying a liquid flow, we get this characteristic formation of what's known as a Taylor cone. And the Taylor cone is seen schematically in this region, and that Taylor cone is pulled into a jet, and that jet is further disrupted into a series of droplets. And this is, again, very characteristic of applying a high voltage to an inlet, to this inlet capillary. The sign of the voltage drop across the atmospheric pressure interface will determine which ion types we're looking at. In this case, you'll see that the capillary itself, the inlet capillary, is the positively charged pole, and the inlet to the mass spectrometer is the negatively charged pole, meaning that we're going to select for positively charged ions. That is, positive ions will be attracted to the opposite sign at the inlet to the mass spectrometer. The region where the droplets are shown in this picture is a very important region, and it is known as the ion evaporation region. The process of ion evaporation takes place in this region, and you can see I've shown schematically some A+ representing an analyte ion which is positively charged. We sometimes see this referred to as the ionization region, but that is in fact incorrect. Ions are formed in solution prior to coming into the electrospray interface, and it's one of the topics that we'll discuss in just a few minutes in regards to the pH of the mobile phase being set to preferentially form the ion types that we want.